All right, hi everyone. Welcome to the final two sessions of the day. These two sessions are special in the sense that these are the best paper and best systems paper nominees. So it's actually best systems paper, and best student paper nominees. The first session, the session that I'll be chairing, is the best systems paper session. I'm Hadas Kaskazit. I'm the general chair of the conference. And we'll just start. So the first talk is Network Offloading Policies for Cloud Robotics, a learning-based approach, presented by Sandeep Chinchali.
Okay, thanks for inviting me. My name is Sandeep, and today I'll be discussing how resource-constrained robots, such as low-power drones, can use cloud computing services for perception and computer vision tasks in robotics. So we believe that tomorrow's robots will face a key dilemma about where they run compute-heavy perception and computer vision models. Ideally, they'd want to run state-of-the-art deep neural networks that are the most accurate, fast, but at the very same time compute and power efficient, but unfortunately this comes with key contending trade-offs. As you can see on the left, today's power-efficient vision models, such as MobileNet, often miss key parts of a scene and are much less accurate than their larger but compute-intensive cloud-grade counterparts on the right. So if a battery-constrained small drone can't scalably run a cloud model, it can still send or offload rich sensory data, such as video or LiDAR, to the cloud, but this actually adds delay due to congested stochastic wireless links. So given the limitations of today's real-world networks, but also the accuracy benefits of cloud computing, the core contribution of our work is to design this offloading neural network logic in blue that decides at every single time step whether a robot should use a fast, local compute model or is highly uncertain and needs the accuracy of the cloud. So despite the accuracy benefits of cloud computing, we seldom talk about the hidden costs of network congestion and cloud communication. As you can see on the left, today's robots are starting to see very rich sensory data, such as 4K video, and it can be used to zoom in on very far-off objects to identify them, unlike HD video in this case. But it comes with the principal cost of high bandwidth transmissions over the crowded internet. And as you can see on the right, in our network experiments using ROS, sending LiDAR point clouds over the network adds to congestion, and our current de facto standards are very bad at sending data. So a receiver in purple often sees less than half the data it was intended to see. So given the limitations of today's wireless networks, but also the allure of cloud computing, we cast the problem of offloading to the cloud as an MDP. So suppose every single robot has a strict budget on how many times it can query the cloud. Then given this budget, but also uncertainty about what the robot will see in the future and how the network will evolve, we have to choose an optimal action of which model is best to use at the current time point. So as you can see, the state of the robot has a new frame of sensory input, which is on the top, and if a new object appears, it can use its local robot model. But if the scene rarely changes, such as in the middle, it can use past predictions to avoid power-hungry inference it just did before. But on the right, if it's highly uncertain, it can query the cloud. So since it's very hard to analytically model both how the network evolves, but also what you'll see in the future, we turn to model-free deep reinforcement learning to learn our offloading decision-making policy. It's control theoretic because a robot needs to carefully manage when it queries the cloud using a strict budget and uncertainty. So the goal of our offloading policy, or RL agent, is to maximize reward. So namely, we want to maximize accuracy, which is on the y-axis of this plot, but at the very same time, minimize the cost of networking and cloud computing, which is on the x-axis. In blue, we show our RL agent, which was tested on a hardware platform on real wireless links, and it was very close to an upper bound Oracle solution in green, but is over 2 times better what you would do today, which is in gray, which is all robot computing. So we strongly believe that tomorrow's robots should have the best of both worlds, both advances in embedded AI, but also in cloud computing, to dynamically choose the right model that makes sense for its current operating condition, but also they should stream very succinct information to the cloud for machine perception. Thanks, and I'm happy to answer questions later.
Okay, our next speaker is Andy Zhang, and he's going to talk about learning to throw arbitrary objects in with residual physics.
Hi, it's my pleasure to present TossingBot. Many pick-and-place solutions today are characterized by slow and rigid movements. This is very different from how a human does picking, which is often fast, fluid, and often involves tossing things around. Can our robots do the same? In this work, we're interested in enabling robots to throw objects to improve both speed and reachability. The task is to grasp arbitrary objects from a cluttered bin and accurately toss them into selected boxes located outside the maximum reach range of the robot. We call our system TossingBot, and while state-of-the-art systems achieve speeds of 200 to 300 mean picks per hour, we achieve more than 500. Throwing is hard because it depends on many factors. For example, pre-throw conditions, like how you picked it up, can influence an object's projectile trajectory. For example, if you grasp a screwdriver by the handle near the center of mass and throw it, it will land much closer than if you had grasped it from the metal tip, which would swing forward and land much farther. Other factors include varying object dynamics. For example, a ping pong ball will land even closer due to air resistance. To address these challenges, we present two key ideas. The first is that grasping and throwing are two tightly intertwined problems that should be learned jointly. This enables our system to acquire its own pre-throw conditions by learning how to execute stable grasps that lead to predictable throws. The second idea is to leverage both analytical controllers and deep learning to develop a hybrid controller for throwing that handles varying dynamics. Specifically, we use a physics-based controller to estimate initial throwing velocities. Then we use a deep network to predict the data-driven residual. The initial estimates from the analytical controller generalize well to new target landing locations, while the data-driven residual focuses on learning to compensate for object-centric properties and dynamics. This combined formulation, which we call residual physics, gives us the best of both worlds and is broadly applicable to other tasks, not only throwing. Here's our system pipeline, which takes as input a top-down RGBD height map of the scene, as well as a target landing location, and outputs dense pixel-wise grasping confidence scores, as well as corresponding throwing velocities to be executed with the motion primitive. The system is modeled with 3 interconnected fully convolutional networks, as well as a physics-based controller, which uses the ballistic equations of projectile motion. And using overhead cameras to track where the object lands, the system improves itself over time through trial and error. During our experiments, the robot takes about 14 hours of real-world training to achieve 85% throwing accuracy, which is better than most of us engineers on the team. The robot also resets its own training so that human intervention is kept at a minimum. And thanks to residual physics, the system is not only capable of generalizing to novel objects, but is also capable of working for new target landing locations not seen during training. So what does TossingBot learn? To explore this question, we extract the mid-level pixel-wise features from the deep network and visualize nearest neighbor clusters in the feature embedding space. Interestingly, this shows that all ping pong balls share similar features. And this is also true for all the marker pens in the scene. These features were learned without any explicit semantic supervision, which suggests that it's possible for robots to discover and learn how to distinguish between different objects on their own, simply through physical interactions. We also study how throwing influences grasping. For example, here's a visualization of the distribution of grasps on one of the objects in our simulation platform. By using throwing accuracy as rewards, our grasping policy learns a smaller and more stable set of grasps that are closer to the center of mass, which leads to more predictable throws. Happy to talk more about this work offline. Thank you.
Okay, our next presenter is Peter Karkas from MIT, I think, actually. He's going to be presenting differentiable algorithm networks for composable robot learning.
Hi, my name is Peter Karkas. I present a methodology for composing robot learning systems. The majority of robots today are built based on the principle of modularity. The system is composed of models and algorithms, like state estimation, planning, and control. However, modular systems are often brittle because of approximations and modeling errors. In response, the modern end-to-end approach directly optimizes for the task objective using deep neural networks. This produces powerful but highly specialized systems that need large amounts of data to train. We want to reconcile the apparent conflict between the two sides and combine the modularity principle with task-oriented end-to-end learning. We introduced the differentiable algorithm network, DAN. DAN has a modular structure of models and algorithms, but at the same time, it is trained end-to-end. The key is to use a differentiable computation graph as a unified representation of both models and algorithms. The computation graph is similar to a neural network, but it also has fixed operations that implement an algorithm, for example, a planner. Because it is differentiable, we can now backpropagate through the algorithm and train models end-to-end. Prior work has developed differentiable implementations of many robot algorithms. Here, we put them together and formulate a system design methodology general to many domains. We perform a case study for visual navigation. These are examples of our system navigating in previously unseen environment, having only a floor map. This is a challenging, partially observable problem. We need to localize on an abstract 2D map, having only images from a monocular camera, showing rich visual features of the 3D environment. Further, we need to navigate to a distant goal while avoiding obstacles that are not indicated on the map. We tried the standard modular system with perception, state estimation, planning, and control. We also tried an end-to-end neural network with a search over the architecture. They both succeed sometimes, but not always. Now, we take the same modular system, but train it end-to-end using DAN. This system succeeds 99.8% of the trials. So why does that happen? Compared to a standard neural network, DAN has a particular structure, a task-specific structure, a prior, that allows learning from much less data. The modular system learns models independently, and it fails because of modeling errors and algorithmic approximations. DAN increases robustness against approximations by training the models end-to-end, optimizing for the task and for the particular algorithms. Our study reveals many concrete ways how this can happen. We show how DAN compensates for an approximate algorithm, an approximate model, or an approximate decomposition. In one example, we choose a short planning horizon and compare learned transition probabilities for a turn action. The independently learned model on the left recovers the true dynamics. The end-to-end model on the right learns to combine the effects of turning with moving forward in a single action. This learned macro action now allows us to plan successfully even with a short planning horizon. We have many more examples in the paper. In conclusion, we proposed a principled methodology for composing robot learning systems. DAN combines the classic modularity principle with the modern end-to-end learning. Importantly, our case study provides empirical evidence for simultaneously benefiting from both. Thank you.
Okay, our next presenter is Dan Bruder. I don't think that was intentional, but it's amusing me, so there we go. Dan is going to be presenting modeling and control of soft robots using the Koopman operator and model predictive control.
So modeling and controlling soft robots is difficult because they have infinite degrees of freedom and highly nonlinear dynamics. So our goal in this work was to develop a way to build models of soft robots that could be used with established model-based control techniques. To that end, we take a data-driven approach. First, because most physics-based models of soft robots tend to either be too simple to capture their dynamic behavior or too complex to be used for real-time control. And the second reason we use data is that soft robots, it's easy to collect data on them because you can safely give them random control inputs without risk of damage. Now, instead of learning a black box model from data, we thought to use the Koopman operator because it provides an explicit linear model that captures the global dynamic behavior of a nonlinear system. And as I'll show, this allows us to use linear control techniques to control a soft robot. So the Koopman operator makes this possible by representing the evolution of the state of a nonlinear dynamical system as a linear operation. So to illustrate how this works, consider some arbitrary nonlinear dynamical system. Its flow map takes an initial state and flows it forward in time according to the dynamics. Now consider some real-valued function. The Koopman operator is defined as the linear operator that composes functions like this with the flow map of the dynamical system. So if we evaluate the function at the initial state, the Koopman operator flows the value of that function forward in time along the trajectory of the underlying system. And so essentially, this lets us linearly compute the future values of functions from which we can readily infer the value of the state. Now, the caveat here is that the Koopman operator acts on functions, and this makes it infinite dimensional. So in practice, we have to settle for a finite dimensional approximation, which we can learn from data. The standard method used to compute a matrix approximation of the Koopman operator is called extended dynamic mode decomposition. And it involves evaluating a finite set of basis functions on time series data points, and then using linear regression to compute the matrix operator that best describes the evolution of those functions over one time step. In this work, we improve upon this standard method by incorporating a L1 regularization term. And this term makes the resulting Koopman matrix less sensitive to outliers in the data. And it also promotes sparsity, which is important for real-time control because it improves the computational tractability. So we use this approach to model and then control the soft robot shown here. It consists of two bending sections actuated by pneumatic artificial muscles, and it projects a laser dot onto a sheet mounted below it. So first, we collected data by measuring the location of the laser dot under random control inputs. Then we used that data to approximate the Koopman operator and verify that it gave accurate predictions over time. And then lastly, we used that Koopman operator approximation to compute online predictions in a closed-loop linear model predictive controller. Shown here are several trials where, using this Koopman-based model predictive controller, the robot is able to successfully track trajectories in various shapes. And what we found is that our controller proved to be roughly 4 times more accurate and 4 times more precise than a comparison benchmark linear MPC controller. And details of that comparison can be found in the paper. Now, unfortunately, today's poster session is over, but if you'd like to learn more about this work, I'd be happy to chat about it at the reception tonight or later in the week. Thank you.
Okay, and the final paper nominated for Best Systems Paper is going to be presented by Nolan Wagner, and it's entitled An Online Learning Approach for Model Predictive Control.
Hi everyone, I'm Nolan, and I'll be talking about our work, An Online Learning Approach to Model Predictive Control. In this paper, we take an online learning perspective to MPC and propose a general algorithm, DMD-MPC, that recovers state-of-the-art MPC algorithms and lets us systematically generate new MPC algorithms. Finally, we verify this approach on a real-world aggressive driving task. First, I'll explain MPC and then its connection to online learning. Let's say we are controlling a robot car around a track. In model predictive control, we maintain an open-loop control sequence, which we then optimize. We then execute the plan on the real system by executing the first control on the system, and then the system will give us back some information for the next step. To bootstrap from the next step, we shift the plan one forward, one time step, and again repeat the process, optimizing the plan, executing it on the real system, and getting back some update information. With that set up, we can now make the connection to online learning. In online learning, we have a learner. Yeah, we'll reset. Can we first check the video's working and then start at the beginning? No, this is just giving me more practice. All right, now we're good. All right, can we start from the beginning? Can we start from the beginning? All right, thanks. Hi, everyone. I'm Nolan, and I'll be talking about our work, an online learning approach to model predictive control. In this paper, we take an online learning perspective to MPC and propose a general algorithm, DMD-MPC, which recovers state-of-the-art MPC algorithms and lets us systematically generate new MPC algorithms. We then verify this approach on a real-world aggressive driving task. First, I'll explain MPC and then its connection to online learning. Let's say we are controlling this robot car around a track. In model predictive control, we maintain some open-loop control sequence, which we then optimize. We then execute the plan on the real system by executing the first control, and then this real system will give us back some information for the next time step. To bootstrap for the next time step, we shift the plan forward one time step. At the next step, we again repeat the process, optimizing the plan, executing it on the real system, and then getting back some information. With that setup, we can now make the connection to online learning. In online learning, we have a learner and an opponent. The learner makes some decision. In response, the opponent chooses a loss function, which acts as feedback to the learner, who in response updates their decision based on the feedback for the next round. In DMD-MPC, the learner sends the current control and future plan to the opponent. The opponent's loss function then measures whether that future plan will remain optimal after applying the current control on the real system. The feedback will then be the gradient of the loss function. The decision update will then work like this. First, we calculate the gradient at the initial plan. Then, we apply a mirror descent step on the plan, which involves minimizing some linearized loss given by the gradient, plus a geometric regularization given by a step size and Bregman divergence. To prepare for the next round of the problem, we shift forward one time step by executing the current control on the system and sliding the future plan forward one time step. So this online learning perspective reveals certain parameters here: control distribution, loss, Bregman divergence, and step size, which, as we'll see, provides us a lot of flexibility. For instance, we can generate general purpose algorithms like online gradient descent with a quadratic divergence in any choice for the rest of the parameters. If instead we use a Fisher information matrix, we get natural gradient descent. If our control distribution instead belongs to the exponential family and we use a Kale divergence, we get a general exponential family control algorithm. If instead we have a special form like quadratic loss and divergence, we get the solution to LQR. If we have a categorical distribution and Kale divergence, we get a discrete control algorithm. With the Gaussian distribution and threshold utility, we recover the cross-entropy method. And finally, with the exponential utility, we recover the model predictive path integral control algorithm. So by simply choosing these parameters, we can systematically generate new MPC algorithms. Finally, we validate our approach on a real-world aggressive driving task, which involves getting a 1/5 scale rally car to drive as fast as possible on a track. In DMD-MPC, the update gradient is ultimately estimated with random samples, in this case a paltry 64 samples, causing a rather noisy gradient estimate. Such few samples might be expected from a low-power embedded system, for instance. In our experiments, we compare MPPI, which has a step size of 1, to the corresponding DMD-MPC rule with a step size of 0.6. With a step size of 1, we get rather unsteady behavior. For instance, the car suddenly turns around over here and goes the wrong way. Here, it drives into this barrier at a moderate speed. And finally, at high speed, it crashes into this barrier. On the other hand, with a step size of 0.6, we achieve smooth yet aggressive driving with no crashes and only slightly worse performance in the state-of-the-art version of MPPI that uses 1920 samples and a trajectory tracker. Thank you all very much, and I'll be happy to answer your questions.
So now we have, I don't know. We started late, so about please come on stage. We have a few minutes for questions before the next session. So if all the speakers will join me on stage. How about you stand in order? So why don't the two of you switch, and then Sandeep will be here. So it's 1 through 5. Questions from the audience? Nick. I think the microphone is coming.
So this is a question for Dan about the Koopman operator. So you're relying on selection of these the bases essentially to parameterize or make the linear representation of the nonlinear space. Does the Koopman formalism give you a sense of whether or not you've chosen good bases or not? Like, can you tell if you've done a bad job of picking the bases?
So for us, we're assuming that we know nothing about the underlying physics of the model. And so if you know something about your model structure, then you can more intelligently choose your basis functions to reflect what the underlying structure is. But for us, we choose sets of basis functions that we know in the limit have a property of being able to represent, certain classes of functions. So in the video, we were using a set of polynomial basis functions because we know that with enough polynomial basis functions, you can approximate, a whole wide class of functions. And the only indication of how good it works for us is comparing model simulations against real data. So that's how we verified it and just compared different basis functions. Yeah.
Other questions? Oh.
I have one for Andy. Maybe I missed it. So your success rate, right, in throwing, like, it would be interesting to know how far you are, and from a product perspective, where you need to be in order to be competitive, and what your approaches would be to actually get there.
Right, so for a more extensive evaluation, those would be some of the metrics that we would start considering. For us, we just evaluated on accuracy, but if we start being more rigorous about whether or not we want to actually deploy this on a real system inside of a warehouse, then those metrics of distance actually landed and the accuracy with respect to the distance also needs to be potentially plotted.
Yeah, another question for Andy. I think you might have mentioned that the residual physics could be used for other tasks. Could you explain if you've done any experiments and what are those other tasks?
So we haven't started exploring explicitly other tasks, but examples would be other forms of dynamic manipulation. For example, sliding or potentially swinging. We have some pretty good analytical controllers that can do some of those things, and it'd be nice to sort of incorporate some learned models on top of that in order to improve the performance, specifically deep learning. Yeah.
So I have a question for all of you. So this is the best systems paper nomination. So I'm going to go with the systems question, which is kind of a general, but I'd like to hear each one of yours perspective about your own system, right? So in systems paper, we like to see kind of what are the general lessons that can be learned from this kind of, from your approach, and what the limitations are, and when will it break? So if you can talk a little bit about that.
Yeah. So the general lesson that we took from here is that you can use principles both from internet congestion control that everyone uses today to connect to the internet, but also advances in reinforcement learning to choose a very succinct decision-making policy that's very easy to train, because we only had very simple actions. Use past predictions, use a local model, or query the cloud. So to some extent, we borrow systems ideas from networking to do this. And some of the limitations are, a natural question is, if embedded AI gets super good, will I ever need the cloud in robotics? So my answer to that would be, let's say you have several robots that are all sending video to the cloud, you could actually get a unique vantage point that you would never get before at the robot. But also, if a robot model is out of date or hasn't been synced with new data, will always be a power for cloud computing. So that's some of the work we're doing in the future.
So one of the things that makes me particularly excited about the system that we built is that we started showing that without any explicit semantic supervision, the system starts learning to distinguish between different object materials and potentially based on their physical properties, because that's necessary to learn how to throw. So I think that speaks out to a broader question in robot vision, which is oftentimes we're funneled into thinking that we need to have our system, we manually define these semantic labels and have our robot systems start to recognize them. But potentially just from physical interactions, these systems can start to learn how to distinguish between objects on their own, and simply by sort of observing the feature embedding space and how they cluster themselves together, which is very interesting. The second part that I want to mention is from building the system, we realized that visual data is not enough. We had our system mostly mapping from visual observations to how to grasp and how to throw. But ultimately, if you had two objects with two different mass distributions but looked exactly the same, the system will start to fail. So it's very important, I think, that in the next step, we also sort of start incorporating other sensing modalities, including tactile or force torque, which I think are all important for systems building.
So in this work, we were interested in developing a methodology for building robot systems that are composable, learn, and they're scalable. So there is this whole conversation going on in the community about whether we should do model-based reasoning, modular systems, or we should do end-to-end deep learning. And we are thinking, how can we do the two things at the same time? So how can we benefit from modularity, at the same time, task-oriented end-to-end learning? So this is what this paper is about, trying to put them together. And importantly, most of our paper, I think, and also is the most important contribution maybe, is trying to understand when and why this is a good idea, and when end-to-end optimization and modularity can benefit you at the same time. So maybe one limitation of this is that, of course, to do this end-to-end training of models, you need to backpropagate gradients through your algorithms, the entire system. So this can be difficult, of course, but there are several ideas that other people are working on that would make it easier. So one of them is that this methodology allows you to pre-train models and get to a reasonable solution pre-training, and then only optimize these components together afterwards, end-to-end. Or other people are working on better ways of estimating gradients through planning algorithms and so on. But yeah, I think that's a difficulty.
So for those of us who are interested in controlling systems where we may not have the most informative physics-based models available, there's maybe two schools of thought on this, and one is that we can learn from data, control policies directly. And I think what I found in this work is that I think it's more powerful to think about learning models, because then what we found is with our soft robot, we could train on random data, but then we're able to perform all of these various tasks that we're not, specifically trained on. And so there's still limitation for any data-driven method that we don't have any information outside of the set of states and inputs that we train on. So there's some sort of fundamental limitation in that sense. But I think it's powerful to learn models even when we go to the full data-driven side of things.
So what we believe is the main contribution in our paper is, through this different perspective of model predictive control, we've exposed certain knobs, like I showed before, control distribution and so on. And what we hope is that by exposing these knobs, practitioners can, by tuning these knobs accordingly, get an algorithm for the problem that makes sense. For instance, if you have a robot maybe navigating around here, but it needs to make it through the aisle and around chairs and people, maybe you shouldn't use a Gaussian distribution because those tails will just not be heavy enough. Maybe you need something heavier like a Laplace distribution, or you need to account for multimodal decisions like a Gaussian mixture model. So this framework that we have naturally lets you generate new algorithms based on just what you desire from your distribution or your cost function, your divergence. So we think this framework is powerful for that. Of course, it's not perfect. There are limitations. For instance, even though it's you can try to cast constraints as extra costs, and it will try to optimize those costs as best as it can by minimizing the constraints. But if it can't, then those constraints are violated. So if you're operating in a very safety critical area like flying a spaceship or something like that, and you absolutely need those constraints satisfied at all time, maybe it's better to stick to a traditional constraint optimization approach. But nonetheless, we think our framework can provide a lot.
Okay, let's thank our speakers. Passing the baton.
All right, thank you, Hadas. My name is Nick Roy. It's my pleasure to chair the last session today, which are the best paper nominees. And our first paper today is the equivalence of the projected forward dynamics and dynamically consistent inverse solution. And João Moura is going to present. João.
Good afternoon. So when designing controllers or motion planners for robotic systems, we often rely on some form of dynamical models to describe their motion. Here, we will focus on two major classes of dynamic formulations. One that deals with motion tasks, such as the movement of the hands or the center of mass of an humanoid. And the other one tackles physical constraints, such as contacts when walking or touching objects. By asking the question, are those two really different domains? And by introducing a reformulation, we prove that in fact those two forward dynamic formulations are equivalent, and so we can potentially use a single approach to tackle both problems. So let's start with the contacts. We typically describe the dynamics of an unconstrained robot by its inertia matrix M. One interesting approach from Magnetically to incorporate contacts in the dynamic model is to define a new constrained inertia matrix MC that captures those constraints. The key idea being to use a kinematic orthogonal projection P to filter the remaining free motion of the robot. There are many works that follow this projection-based dynamics approach when working with real robots having to deal with contacts. However, there are multiple constrained inertia matrices to choose from. So we start by reformulating them, by proposing a reformulation that unifies all previous expressions in one by expressing those two terms as a function of a common free matrix R. Why? First, this unification makes all our future derivations valid for all the previous expressions. And second, if this R can be any other matrix, then we can try to find an optimal one. So consider a arm sliding in a rail as an example, where here we plot the time evolution of the condition number of all previous constrained inertia matrices. If we desire to obtain the lowest possible condition number for better numerical stability, we can now find the respective R that optimizes it, leading to this lower bound curve. So let's now consider motion tasks or behaviors. For example, balancing a glass of water while walking or having a compliant behavior for safe interaction. In that case, we can write the equation of motion in the task space by defining a task space inertia matrix MX and map that to the configuration space using the operational space formulation from Predictive. In our work, by considering a broader class of task-based constraints, which essentially include both motion tasks and physical constraints, we prove the analytical equivalence of the operational space formulation, which is typically used for tasks, and the just reformulated projection-based dynamics approach, which is typically used for constraints. And so on. Why does this matter? The key idea is that this equivalence can help us build a bridge between their associated body works of research. For example, there are two separate parallel works that propose different operational space controllers with rigid constraints, with different expressions. In the first, Sapio and Predictive take the operational space formulation and add equality constraints. And in the second, Mystery and Rigetti start with the projection-based dynamics and add the task space motion. By using our finding, we can easily show through simple algebraic manipulations that those two controllers are also equivalent. But bear in mind that these two works are particular instances of two families of research work, which include various other controllers, motion planners, and even proofs on stability and robustness. Using our finding, we can now potentially adapt or transfer results from one formulation to another. And ultimately, this will improve our understanding on these complex systems. Thank you so much for your time.
All right, I'd like to welcome our next speaker, Mohan Sridharan, speaking about common sense reasoning and knowledge acquisition. Mohan.
Okay, cool. I'm going to talk about combining common sense reasoning, knowledge acquisition, and deep learning. The motivation for this is that deep learning these days presents the state of the art for several different problems in robotics and AI, but we all know that it has some common limitations, namely that you take large labeled data sets, and you need considerable computational resources, and also the internal representations and reasoning mechanisms of the models you learn are difficult to interpret. So here we have an attempt at an exploratory study to say, can we draw inspiration from research in cognitive systems, specifically 3 key principles. First one, that representation, reasoning, and learning need to be tightly coupled with each other, and they are also ongoing and continuous. They feed and off of each other. Second, that you can reason with incomplete common sense domain knowledge, and you can use that reasoning to guide your learning to be more efficient, but also you can do cumulative learning. So as you get more and more data and information, you not only do it efficiently, but you can also learn to make better decisions and also learn more abstract concepts. Third, that for any given task, whether it's learning or reasoning, you can automatically figure out, or you should be able to automatically figure out, what parts of the world are relevant, and you want to only reason or learn about those things. So the attempt here is to computationally model these principles and to do so in the context of scene understanding. And as we will see on the next slide, it is about predicting stability of object structures and partial occlusion of individual objects. So we take these simulated scenes, which will come up shortly, and what you will see in the simulated scenes are these objects stacked one on top of each other and on the ground. And so what you have is a robot that's going to make predictions on stability and also about occlusion, and to use that to also say clear up clutter, so to speak. So a traditional approach would take this, do the 3D point cloud, extract some visual features, and then run it through a CNN. So in between these 2 components, we now embed this common sense reasoning component with both non-monotonic logical reasoning and inductive learning. So what we do here is we take these basic object attributes, we also infer some geometric relations, and we encode that. But in addition to that, we also encode default knowledge and other common sense knowledge if you know something about the domain. For instance, you might know that a large, heavy object placed on a small object is likely to topple over, but you may not know that, for instance, a cube in the second image, if placed on top of a sphere, will not stay stable. So what you want to do is you want to reason with this kind of knowledge, and you use non-monotonic logic. Unlike classical first-order logic, you don't have to think about things as being just true or false. They can also just plain be unknown, which means you don't have to make commitments unless you are forced to do so. And second, you can easily withdraw previously held conclusions, right? And these nice, appealing principles are used to reason with this knowledge. And if you can, then you just stop there. But if there are images or image regions in which you are not able to make those decisions, only those are focused on the CNN. And because we said we're going to couple reasoning and learning, anytime you send a sample to the CNN, you're implicitly accepting that your reasoning cannot deal with it. So in addition to just learning with CNN, you also take those same samples and induce additional rules with the inductive learning, and it feeds back into your knowledge representation system. And this gives you at least 3 key advantages. One, the underlying logical system lets you come up with explanations and also answer hypothetical questions. What if something happened, right? The second is, second and third are quantitative in nature. So if you look at that plot there, so if you compare, say, the red and the blue or the green and the black, you see that for any given accuracy, you achieve that with a much smaller number of examples. This is for a simple simulated domain. If you take other robotics domains and stuff with more complexity, the difference is more pronounced. But it still scales because of the principles of relevance. The third thing is that because planning and learning are tightly coupled with each other, anytime you learn, you also get better decisions. So for that set of toys at the bottom here, so if you wanted to manipulate that red object and move it to a different location, initially you start with around 60 or 70 odd plans, many of which are incorrect or suboptimal. But instead, if you learn over time, you are able to come up with 3 plans which are minimal and correct. And there are additional details in the paper about non-monotonic logic and other aspects, but I'll stop here. Thank you.
Thank you, Mohan. So it's my pleasure now to welcome our 3rd speaker, Chris Hauser.
Thank you. So this is work with my student Fan Wang. We're interested in optimizing the packing density of objects into orders. We are sponsored by an Amazon Research Award, and we want to avoid situations like this. So in this paper, we're interested in a kind of tweak to this problem, a little twist, which is that we don't know the arrival order of the items that are being given to us. This is a case that's common in fulfillment of Amazon orders that might go out to a fulfillment center. These robots will bring some shelves around to some sort of packing station, either a human or a robot packer, which then needs to put the items into a container to which then gets shipped out. So here you don't necessarily control in which order these robots arrive at your station. This is also a common problem in freight co-loading or less than truckload consolidation, where smaller loads will come to some sort of distribution center to be loaded into a larger freight truck. You may not be able to control in which order these smaller loads arrive at your distribution center. So this is a kind of middle point between offline packing and online packing, which are traditional bin packing domains. In this case, we want to still verify that a container can contain the load, but we don't know necessarily the order. The first variant of this problem that we introduce is called NDOP, or non-deterministically ordered packing, in which case the sequence that the objects arrive gets revealed to you after you've verified the container is feasible for all possible orders. In the second case, we have quasi-online packing, in which you have to pick a location for the item when it's revealed for you, but you don't know in which order the subsequent items are going to be given to you. What we do in this work is we build off of some of our previous work in 2019 ICRA, where we assume that there's an offline planner available to us, which we call the Oracle. This Oracle in this paper is using stability constraints as well as loadability constraints to verify that a robot can load these items into a given container. So we assume that all of the Oracle's job is to handle all of these continuous constraints. To solve the NDOP problem, we don't want to necessarily solve offline plans for all n factorial orders of items that arrive to you. So instead, what we do is we introduce a concept called the constraint dependency graph. For this, you take a given plan, and then you can come up with an order, basically pairwise constraints about which items need to be loaded before which other ones. You can see these in the gray boxes up here. And our planner essentially uses these constraint dependency graphs to try to come up with a minimal number of plans that covers all possible n factorial orderings. What's interesting here is that the solver inherits the completeness of the oracle. So if the oracle is complete, the planner is too. Empirically, even though in the worst case this is still an n factorial algorithm, the number of plans that we have to solve in practice is very low. So for the APC or YCB data sets, we sampled 1,000 random object sets. If we have 5 items, we have to solve on average 1.6 plans per container, which is much less than 120. For the quasi-online packing solution, the solution is actually, interestingly, a policy tree. For every single item that gets revealed to you, you have to be able to place it in a given location. And so we still enumerate all of the different leaves of this policy tree, which is a factorial number of leaves. But what our algorithm does is that it actually very aggressively chooses to reuse plans that were generated before. So for example, when this banana gets revealed here, 3 of the possible future sequences can reuse plans that were generated in the previous enumeration of this tree. If the banana is revealed after the pliers, that's what you do, but if the banana is revealed first, this is what you do, and so on and so forth. So it's actually quite a large tree. But in any case, we proved that in this paper, the QOP problem is at least as hard as the NDOP problem. The solution is always correct, although the algorithm is incomplete, even though the oracle may be complete. And there's a lot of interesting empirical performance. It basically is quite tractable with small numbers of items, but it tends to break down for larger numbers of items. And there's a lot of interesting theoretical results. I messed up with this poster, unless you can time travel, so I'll talk to you about this later. Thanks.
Thank you, Chris. It's now my pleasure to welcome Ziyu Ren, who's going to tell us how to make tiny little jellyfish robots.
So, hello everyone. My name is Ziyu Ren from Max Planck Institute for Intelligent Systems. I will present our work on a jellyfish-inspired soft Milliswimmer. A soft body designs enable new capabilities to robot. Inspired from octopus and squid, a soft body enables the robot to achieve shape deformation, to achieve diverse different behaviors, to achieve multiple functions, and to achieve a safer human-robot interaction. A soft-bodied baby jellyfish is one of the most widely spread creatures around the ocean. It adopts a paddling motion to propel at millimeter scale. Inspired by this efficient swimming propulsion strategy, we developed a magnetic soft Milliswimmer that has the same size and can achieve the same motion as a real animal. The real UFO jellyfish has 8 arms, which are called lapis. We keep this design in our robot. Our robot is composed of 2 parts: the 8 magnetic lapis that can bend under external magnetic field, and the passive non-magnetic polymers. The overall size of the robot is only 5 millimeters in diameter. So to fabricate such tiny robot, we first form a thin layer of magnetic soft material on a flat plate. In the second step, we use an UV laser to cut the lapis out from the plate. And in the next step, we use a water droplet. We use a pipette to drop the water droplet at the center of the magnetic lapis, and due to the surface tension, the robot will be wrapped up in this shape. and we freeze the water droplet to keep the shape of the robot and apply a uniform magnetic field to magnetize the material. This will create a magnetization profile that is very critical to achieve the deformation under the external magnetic field. In the last step, we fill the gaps between the robot with non-magnetic polymers. The robot swims in a coil system that can provide arbitrary direction of magnetic field. By applying an oscillating magnetic field along the body centric axis, the robot can realize propulsion. By rotating the direction of the magnetic field, the robot can be steered. The robot swims so fast, so we just slow down the video. We apply two kinds of control signals to evaluate the propulsion performance of the robot with different amplitudes. And both the modeling and the experiments demonstrate that the robot can achieve the highest swimming speed with a larger beating amplitude, and the optimal frequency is between 10 to 20 hertz. We also demonstrate multiple functions towards medical applications on our robotic platform. In the last video, I will show you the robot can trap the cargo during its propulsion using the fluid flow generated around its body. And this function will be useful to transport drug in complex environments. In the right video, we show that due to the softness of the body, the robot can clog a tube. This function will be useful to clog a fallopian tube in the future for birth control. And another example is that we can use a catheter to send the robot into the bladder, and we let the robot to swim upwards and finally patches to the cancerous tissue to release the drugs for a long time. As a fourth step, in the right video, I will show you that the robot can swim in a model bladder and finally patches to the target surface here, and its swimming is traced by the ultrasound. So in this study, we propose the first untethered magnetic salt milliswimmer that can mimic the swimming of a euphor jellyfish in the same length scale. And we demonstrate multi-functions towards medical application using the shape deformation. And the robotic itself is a very good platform to help us understand the biological relevant questions. And thanks for your attention.
Thank you, Ziyu. And our last speaker of the session today is Ilan Farhajinov, who's going to tell us how and why to keep our chin up.
Hello, my name is Ilda. I'm from Queen Mary University of London. Today I'm going to explain you why head stabilization behavior in animals and robots is important for verticality estimation. As you see here, many animals, they stabilize their head, and they can do this efficiently even without any visual feedback. Should robots do the same? Why it is important? Traditionally, robotic systems rely on ground information for stable locomotion. And more recent robotic systems start having their head stabilized. But why do we need to do this? Is it important? Humans also stabilize their head. And for humans, it is important for motion planning and stability. To investigate, the goal of this study is to investigate the importance of head stabilization for verticality estimation. Knowledge of gravitational vertical is important for stable locomotion, and otoliths located in our vestibular organ are responsible for this. In our work, we propose a model to demonstrate the importance of head stabilization behavior for verticality estimation. The model is composed of a head, trunk, head stabilization controller, and a spherical pendulum to mimic the behavior of an otolith organ. Our vestibular sense can be tricked when our head is tilted and accelerated at the same time. This is called gravity inertial ambiguity. But if the head is stabilized, we can assume that pendulum or otolith can act as an accelerometer, and then a simpler linearized model can be used. We developed a model which composed of head and pendulum coupled dynamics equation of dynamic and motion and head stabilization controller. Our system can move freely in 3D space, and the model is nonlinear, but it can be linearized if we consider a stabilized head. We wanted to know if angular orientation of the head with respect to the vertical is observable based only on the pendulum measurements. To do that, we ran a numerical algebraic observability test, and we found out that verticality is observable only when the head is stabilized. To further develop our verticality estimator, we consider the following model assumptions. Our head should be close to upright orientation, so it should be stabilized. Then we can use a linearized model for controller and observer. And then a separation principle will be valid here, so we can do simultaneous stable control and stable estimation. You can see the overall diagram on this slide. To investigate the performance of our estimator, we ran a simulation study for two cases. Case 1, when head was not upright, and second case, when head was upright stabilized. Simulation demonstrated that verticality estimation error was significantly reduced when the head was stabilized in upright orientation. Finally, we have developed a robotic prototype to model our system. The model was based on a liquid-based inclinometer, and we ran an experimental study to investigate the performance of our head stabilization controller in two conditions, based on the sensory input only and based on our observer, which is shown on the right video here. The head was stable with the help of our verticality estimator. The video on the left shows the performance without our observer, so the system was overall unstable. The plot here demonstrates how easily this system can go unstable without our controller. In this study, we demonstrated the importance of head stabilization behavior for verticality estimation. The results of this study are applicable to a wide range of robotic systems with a moving frame of reference. Thank you.
Thank you, Ilan. So now I'd like to invite all 5 speakers to come up on stage for the question and answer panel. And if you can pass the microphone back and forth as needed, that would be great. So, questions for our speakers? Oh yes, if you don't mind standing in the order. So, Ilan, you would be at the end. There we go. All right. Do we have any questions? All right, well, I have one for ZU, which is the length scale of your jellyfish is about 3 millimeters, correct?
The diameter is 5 millimeters.
So there's relatively few vessels in the human body that are 5 millimeters across. So if you want to do drug delivery or blockage, how small are you going to be able to get your jellyfish?
Actually, that depends on your scenario. If you want to use it in, for example, the bladder, the 5 millimeter is okay. However, if you want the robot to swim in a blood vessel, it's hard. I have to admit it's hard to swim in the artery because the blood velocity is very high. However, if you want the robot to be used in wing, the blood velocity is relatively low, and the average blood velocity should be around 13 to 15 millimeters per second. And our robot, the peak velocity of our robot is around 14 millimeters per second. So it's possible to use our robot in wing. And the average diameter, the inner diameter of the wing is around 5 millimeters. So it will fit our robot. And we can also push our method to make a smaller robot to maybe hundreds of microns. So that's enough to swim in wing, in blood vessel.
Great. Questions? I know it's the end of the day. We're all looking forward to the reception. All right, maybe what I'll do is wrap the session up with the same question that had us asked the previous session, which is, you've demonstrated remarkable results in lots of ways, which is great. What's the dirty laundry? Where does it break? What are the limitations? Joel, I'll start with you. And take the microphone, please.
So in my case, in this work, it's hard to say in terms of limitations because I'm not proposing a new method. I'm basically pointing out that there's two major or the two motion representations out there, and there's an equivalence in their fundamental equation of motion. So this is a shout out that if you're using either of them, just go check the other one. Probably there's work developed already in that area. one of the future, so we prove analytical equivalence. It doesn't mean numerically one is better than the other one. So something that I want to do as future work is to investigate further and to actually see in terms of speed of computation and numerical stability if we can gain something from one of these formulations, and further to look into other works to see if there's other interesting findings as a result of these works that we can extend. I don't know if I answered the question.
Thank you. Mohan.
Thank you.
So I will do something similar. I'll talk about lessons I learned, right? And there will be some limitations as well in there.
Great.
So the thing that I found fascinating working with a student on this project was, one, that it was nice to see that things that would be considered sort of old school AI combined really nicely to provide the kind of knowledge that can help learning systems, data-driven systems work very well. It was a lesson that is, yes, reinforced, but it was still worth reinforcing, and that was nice. At the same time, in terms of limitations, what I also learned is that, like, you have to be careful about how you represent and reason with this knowledge. And if you're not careful and you don't do things properly, you can't blame the knowledge representation system. It's human error. So I learned how to do those things better. So I'm going to just say that.
So in terms of, I guess, overall lessons learned, I think one really important lesson that maybe is relevant to others is that with robotics, you can really teach old dogs new tricks. I mean, packing is a really old problem, but I think we've identified many new variants that are coming out of real robotic systems, which I think is pretty interesting. In terms of dirty laundry, scaling in the presence of non-determinism is actually quite bad. So if you are looking at 10 items, you have 3 million plus possible orders, and it can take quite a long time, over 24 hours, to compute a verified solution. So there's a lot of trade-offs between theory and practice, and basically if you just picked a bigger box, you'd probably solve it basically instantaneously. So
the same question? Yeah, I think the contribution of my work is straightforward. Our goal is to make a real useful robot can be used in medical applications, because we don't believe after 100 years ago we still need to use a catheter, we still need to open the human body to do the surgeries. And I think in the future we should still stick on improving the performance of the robot to make it swim faster, to make it transport cargoes better, and yeah, and then we should do the experiments maybe in environments that is more closer to the real environments to achieve multiple medical applications in the future. Yeah.
In terms of contribution in my work, we had a contribution into biology, so we show why head stabilization behavior is important in biological systems. And bigger question is, do we need to it in robotics? So that may be a contribution, but at the same time a limitation, because we should not always take straightaway approaches from biology and copy these to robots, because with the current development of technology, maybe we can do better than animals. And a more specific limitation of the study I had, the model we developed had several key assumptions, and these assumptions are relatively critical for stability of the system.
All right, very good. So unless there are any new burning questions, perhaps we will end here and thank our speakers once again.